Okay, most of these we're just going to talk about, and you need to be aware of them and when you would potentially use them. Okay, so we've got here a scatter plot. We're going to talk about this in detail when we make it to chapter 10 at the end of the semester. But a scatter plot is a chart that plots paired quantitative data. Okay, a chart that plots paired quantitative data. Okay, so here we talked about this example already, volume of the brain versus IQ score. And so we wanted to know if there was possibly some pattern. And so each dot represents a subject's brain volume and their IQ score. Okay, so we've plotted all of those things to see if there's some pattern there. Okay, do you think there's a pattern here? No. Okay, all kinds of data. It's a very simple tool, but also very, very, very powerful. Once we determine if there's a pattern there, then we can try to come up with an equation that models the data so that we can use that to make predictions. But again, we'll talk in detail about that in chapter 10. So if you got two quantitative paired variables and you wanted to show what that data looked like, a scatter plot would be appropriate. Okay. All right, use the volumes and weights of regular Coke. Does there appear to be a correlation between volume and weight? What else is notable about the arrangement of the points, and how can it be explained? Okay, so here we have a scatter plot. All right, when we look at this scatter plot, do we think that there is a relationship between volume and weight? Yes, okay, there's certainly a relationship between volume and weight. It looks like it might be a linear relationship, approximately. And we can say as volume increases, so does weight. Okay, so all of those things. But the other question is, what else is notable about the arrangement of the points? Would you say outliers? Okay, yeah, there was an outlier here. I suppose we call that one 11.8. There's a low ball one. Okay. Okay. All right, but yes, there's something kind of weird going on here where these dots are grouped this way. Why do you think that is? Not why is it weird, but why is it like that? Well, it's actually a lack of variation, really. It probably has a lot to do with the measuring instrument. How precise was that measuring instrument? Could it make a distinction between 12.1 and 12.13? And it looks like whatever measuring instrument they used couldn't. Do you see that? Okay, it's either 12.1 or 12.2, but there's nothing in between. Now, we know that there are probably volumes in between there, but maybe they were using a graduated cylinder or whatever, and that's all they could do. Okay, so it looks like there could have been a problem with the preciseness of the measuring instrument. All right. Another time that this happens, and I keep talking about the project and thinking, wow, I wish I'd said this before. But students, when they collect age data, they would do categories instead of letting the respondents just say what their ages were. And so then when you want to talk about the average age, you don't have any real age data. The best thing you can do is an estimate. Does that make sense? All right. So, when we can, we want our data collection to be as precise as possible. Otherwise, you end up with these kind of weird gaps between your values, and it kind of throws everything off. Okay. At best, this is an estimate. All right. Questions about that? Okay. Very good. Okay, the next chart is a time series graph. And this is just a graph where we want to see what data looks like over time. Okay, we've collected data at various intervals of time, and we chart it to see what that looks like. So here we have the total number of home runs in Major League Baseball. We've got home runs over here, and we've got the year. So in short, what could we say about the trend of the number of home runs in baseball? Okay, looks like, okay, from 1990 to about 2000 or so, we had a steadily increasing pattern, right? But then after that, looks like we're starting to taper off or even have a slight decline. Yes, I think that's what happened.
There's quite an argument actually going on now. Was it just steroids or was it a combination of things? Several expansion teams came into the league, which other teams for expansion teams have to give some of their players up to the expansion draft against the league overall. The stadiums that were being built were generally tiny.
Okay, that's a lot. I wouldn't know all that.
Well, I didn't know all that until just a little while ago. It's a big argument.
Okay, very good. All right, so there's some things going on we know now that may be changing the number of home runs that people are getting. Okay, excellent. Any questions about the time series graph?
This is a graph that is over time.
It shows the changes in data over time. Okay. Shows the changes in data over time. All right, the stem and leaf plot. I want to take my time and talk about this one. This is another display for quantitative data. And basically, with the stem and leaf plot, we're going to break our data into two pieces, a stem and a leaf. Okay, the leaf is going to be the very last digit. Okay, stem and leaf plot breaks data into two pieces. Okay, the leaf is going to be the last digit. And the stem serves as a category. It's everything else. Okay, so it's the remaining digits. I guess I should have defined this one first. All right, so if I take a quick scan of my data here, looks like the values go from about 120 something to 140 something. Okay, so I'm going to let my stems be 12, 13, 14, and 15. Did we say 150? No. Okay, so 12, 13, and 14. So the 12 represents the 120s. The 13 represents the 130s, the 14, the 140s. And it would be nice if we had our data sorted, and I think I can do that quickly, but then I won't be able to see it, so it doesn't matter. Okay, so we'll just go through here and place the values. We just write the leaf with the appropriate row. So for instance, we've got 133. I'm going to put 3 here. There's the 130. Here's the 133. We got 136, so I just put a 6 there. 126, we put a 6 there. Okay, 137, 138, 132, 135, 136, 36, 128. Okay, 140. Okay, that's the first row. Okay, did I miss it? In the first row? Okay. Yeah, I did it by the first row. Okay, then we got 140 again, 135, 137, 139, 134, 145, 143, 131, 140, and 143 again. Okay, I think I got it right. So these are breaking distances. All right. So what are some benefits of this stem and leaf plot? Luann is like, I have no idea. What is it? Okay, all right. We've quickly made a distribution, right? We can see that most of the values fell in the 130s category. Okay. All right, I added something else. It wasn't difficult to do. All right, we could do it pretty quickly. And what else? What is that? I don't know. We'd have probably a pretty good idea about where the average is. And I should say that, if we were done with this, we would have gone back and sorted the values, cleaned this up, made sure even the leaves were in the right order. What's different from this than from a histogram? You can see the values, right? Not only can we see the distribution, but I can tell you what the values are. When I look at this, I can tell you there's 126, 128, 133, 136, 137, 138. Okay, so you should be able to look at a stem and leaf plot and reconstitute the data. Okay, tell me what the data values are by looking at the plot. All right, and sometimes, depending, we might need to do a little key for our data. Like, for instance, if these were supposed to be, let's say this was really 12, 13, and 14, and these were decimal places, then I might have a key over here that says something like this. So you would know that. Okay? Does that make sense? All right. Otherwise, we just assume that you write it, and that's the number that you get. Okay. Questions? Oh, so lots of variations on the stem and leaf plot. We can have a back-to-back stem and leaf plot. So let's say we had a gender thing going on, and I wanted to compare. Then I could put the female leaves over here, and then draw a bar right here, and put the male leaves here. So we got it back-to-back. We can compare the data. Okay. Also, if we had a really large number of values, we might break the classes up into two stems each. So that might look like 12, 12, 13, 13, 14, 14. And for the first row, I would do leaves of 0 to 4. And the second row, I would do leaves of 5 to 9. All right, so we'd get 6 and 8 again. Okay, I've got 1, 2, and 3, and 4. I'm kind of sorting, trying to. We've got 2 5s, 2 6s, 2 7s, an 8, and a 9. Okay, so same data, except we use 2 stems per class. All right. Questions about that? Okay, very good. All right. A Pareto chart is a chart for qualitative data. Okay, this one is for qualitative data. And it arranges, it's basically a bar chart. Okay. It's a bar chart arranged in order of descending frequency. Okay. So that means it's the bar chart is arranged in order of descending frequency. We have the class that has the largest frequency. That's going to be first. And then it goes down from there. Okay. Pareto chart is a bar chart with the bars arranged in order of descending frequency. All right, so here we have instruction times for school children. Okay, and I've got my axes labeled. I've got a title. Okay, and we can quickly look at this and say what? Who had the longest instruction time? China. Okay, we've got it arranged that way. You know, when you have the numbers even on the spreadsheet, when I had the numbers listed there together, these numbers are pretty close, and it took a second to pick out the one that was most frequent. Do you all have this? Oh, okay. 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 I'm sorry about the chart part. Sorry. I will add this to D2L and then you'll have it there. Okay. The author tends or seems to be more in favor of Pareto charts than he used to be. And, you know, not everything, the next thing we're going to talk about is a pie chart. Not everything is appropriate for a pie chart, okay? So you really need to think about the purpose of your chart and if that type of chart is appropriate. So if we just want to see which one occurs most often, a Pareto chart might be the best way to go. Okay, pie chart. All right, a pie chart, really, its purpose is to show how each category contributes to the whole. Okay, how each category contributes to the whole. If you have qualitative data, and sometimes quantitative, but if you have qualitative data that makes up an entirety, and you want to say, okay, this much of example, and this much is made of this, or whatever, then a pie chart would be appropriate. Okay, pie chart's purpose is to show how each segment contributes to the whole. So here we have an example. The numbers of motor vehicle occupants killed in crashes in 2005 are shown in the table. Use a pie chart to organize the data. How many degrees should be used to represent each segment? Okay, so, you know, here we have like the total number of occupants who are fatalities, we'll say. Okay, and so if I want to know how many of those came from car crashes, how many of those came from trucks, and how many came from, I'm taking all of the entirety of the fatalities and I'm distributing it to categories. A pie chart's appropriate for that. Okay, so that's what we have here, and of course you see a little picture there of what the pie chart looks like, and you'll see in the video when you get ready to do your M&M pie charts how to make a pie chart like this. We don't do these things by hand because it's 2013. Okay, we use computers, and so that's what you'll do. All right, but it's still important, you know, to check Excel and make sure that it's telling us what we need to know. So we're going to very quickly do that. We want to come up with the percentages, and we want to come up with the number of degrees that each category should contain. So we get, for percentages, of course, we're just going to take the frequency and divide it by the total. Okay, however many people, or what the total of our sample is. And then for the degrees, because this gives us a percentage, or well, if we really want a percentage, we have to say times 100%. Okay, and then for the degrees, we do the frequency over the total times 360 degrees. Okay, we want to know what portion of the 360 degrees that makes up a full circle do we need to assign to each category. Okay, so our total number of fatalities, very good, 37,594. Okay, we're going to take each frequency, divide it by that number. Okay, what'd you get? Okay, 49%, very good. And then, okay, 37%. Very good. Okay, And you'll notice these numbers should match with, if Excel did it correctly, what's there in the image for the little pie chart that I made. And I think the most important thing to display on a pie chart is the percentage. It gives you options to do the frequencies and things like that, but really we want to make sure we display in a pie chart percentages. Okay, if I want to do my degrees, then I would do 0.49 times 360. Oops. Say it again. Degrees. Okay, 0.37 times 60. Say it again. I'm sorry. Okay, and then all right, and all of these should add up to approximately 360 degrees. We have some round off error. Okay, but if I ask you how many degrees should be used to represent the category of motorcycle accidents, you should take the motorcycle accidents, divide it by the total, and then multiply that by 360 degrees. Let's talk about this before we stop. Then does it make sense if we go back and think about that school, the number of instructional hours in the school day, does it make sense to use a pie chart for that? No, okay? Those hours don't make, when we put them together, they don't make a whole anything, okay? So it would not be appropriate, even though, it wouldn't be appropriate for us to use it for that type of data, okay? So think about it, what's appropriate, what's not, and that'll be it.